What if I told you that heat doesn't flow smoothly and energy moves in packets? This single idea changed physics forever, giving birth to quantum mechanics. Welcome to Simple GAN, where today we decode Planck's law, a fundamental rule explaining how hot objects emit light and energy. By the end of this video, you will understand what Planck's law says, why classical physics failed, and how this law changed science forever. Before Planck's law, we must understand blackbody radiation. A blackbody is an ideal object that absorbs all radiation and emits radiation only based on temperature. Picture a furnace. Heat it slowly, and it glows from dark red to bright red, then yellow, and finally white. This happens because hot objects release energy as electromagnetic waves, known as thermal radiation. Classical physics had equations, but they failed badly at high frequencies, predicting energy should go to infinity. This failure was named the Ultraviolet Catastrophe, and that's where Max Planck entered the stage in 1900. Planck was desperate. Nothing worked, so he tried something radical. Energy is not continuous. It comes in packets called quanta. Instead of flowing smoothly like water, energy jumps in steps. He wrote, energy equals h times frequency. Here, h is Planck's constant, and frequency is the vibration of radiation. Higher frequency means more energy per quantum. This single equation laid the foundation for quantum physics, atomic theory, sensors, cameras, and solar cells. Planck's law tells us the amount of radiation emitted by an object depends on its temperature, wavelength, and energy quantization. It gives the exact distribution curve of radiation. As temperature increases, radiation increases. Hotter objects emit shorter wavelengths, causing the peak to shift toward blue, while cooler objects emit red and infrared. Crucially, Planck's law shows there is no infinite energy at high frequencies. Classical physics said energy increases forever at shorter wavelengths, but Planck said, no, energy rises, peaks, and falls. This comparison shows the classical curve was wrong, while Planck's curve was perfect, fixing the ultraviolet catastrophe. Let's bring this into real life. Example 1. The sun. The sun emits like a blackbody, with its peak output around 500 nanometers in the green-yellow zone. That's why our eyes evolved to see visible light. Example 2. Thermal cameras. Thermal cameras detect infrared radiation, and Planck's law converts this radiation into temperature readings, creating heat maps. Example 3. An incandescent bulb. A hot tungsten wire glows, and its color depends on its temperature. Example 4. Astronomy. Star color tells us about their age, temperature, and size. Blue stars are hotter, red stars are cooler. Planck didn't know it, but his theory led to Einstein's photoelectric effect, the Bohr atomic model, and quantum mechanics. It also paved the way for lasers, semiconductors, computers, and smartphones. Modern technology exists because energy is quantized. In summary, Planck's law tells us energy behaves in packets. Radiation depends on wavelength and temperature, and there's no infinite blow-up at UV. It marked the birth of quantum physics, showing that our universe obeys discrete rules. If this made sense and helped you, please like, share, and subscribe to Simple GAN. Drop your questions below. We reply to every single one. This is Simple GAN, explaining science simply.